I just want to start by thanking the collaborators, so Nicole Younger-Halpern from Harvard, Hugo, Alex, and Crispin from the group in Cambridge, and Seth Lloyd from MIT. And I also want to thank these guys up here for funding this work. And the title of today's talk is The Usefulness of Negativity, Quantum Advantage in Post-Selected Metrology. So I'm going to tell you about how this quantum resource called negativity can help you in various sensing tasks. And if you find this interesting, you can find our full paper under this Nature Comms numbering here, or on the archive under this archive number. So yeah, let's get started. Let's see. So just a brief outline of the talk. I'm going to start by telling you what metrology is about, and especially what parameter estimation is about. So we're going to start with a short review of parameter estimation. And then I'm going to tell you about something that maybe everyone isn't super familiar with, but it's something called post-selected parameter estimation. And after we've done that kind of background, I'm going to introduce a mathematical tool, which is a quasi-probability distribution discovered by Kirkwood and Dirac many years ago. And then I'm going to use this mathematical tool in order to prove that you can get a non-classical improvement of metrology when you post-select parameter estimations that are made with quantum systems. So this is just a brief outline. So let's get started. Metrology is the study of how to measure or estimate things. So it really encompasses a lot of what we know of as physics. So let's start with this review of parameter estimation. So what is it to physically estimate something? And I'm going to do this with this kind of little toy model here. That's a very general model. This box here is some kind of system or experiment where you know everything except for one unknown parameter, theta. So if this is a classical system, maybe you know exactly what the system is, but you don't know the temperature of one component. So theta would be the temperature. Or if this is a quantum system, maybe this is a quantum computer that's conducting an algorithm, and you know everything about the workings of the quantum computer except for the phase of one of the gates. And you want to find out what this unknown parameter is. So physically what you do is that you prepare an input. You can have different inputs. I've labeled them with J. And in the most general kind of parameter estimation scenario, you could envision creating a probability distribution over different J's, so different input states, and sending them into the experiment to see what's going to happen. And when you've done that, and you've seen what's going to happen, you're going to get some outcomes that I've labeled with small m here. And as you repeat the experiment, you will build up measurement statistics. So you will see outcome 1 happens with some probability, outcome 2 happens with some other probability. And if you've designed your experiment in a good way, then these probabilities will depend on this unknown parameter theta. And then you can use statistical techniques like the maximum likelihood estimation technique in order to use this experimental output data to estimate, to make a guess of what the unknown parameter is. And a measure of how well you've managed to do this is the variance of this unknown parameter. So the variance of your guess. If the variance is very small, then you're going to be able to make accurate or precise guesses of what theta is. And if the variance is very large, you will do unprecise guesses. So we're going to focus on trying to make this variance small today. That's what research in metrology is about. And in order to do that, we're going to have to talk about an information quantity. And just to make sure that we're all on the same page, I'm going to spend a little bit of time in the beginning here to go through the algebra that you need to see in order to appreciate what this information quantity is. And I really don't take pride in like going through derivations in talks, but I think that this particular one is so simple and it's very explanatory in terms of understanding what this information quantity is. So I'm just gonna do it. We need one assumption, and the assumption is that the way we're gonna estimate theta is in a way so we don't get any bias. In kind of statistics language, this means that the expectation value of our guess is going to be equal to the true value of theta. Or in like other words, if you ran your experiment an infinite amount of times so that these probabilities of various outcomes that you get, they correspond exactly to your theoretical model, then in this infinite trial scenario, you will be able to guess the right value, the exact value of theta. And this is really not a strange assumption. It can be shown that in most kind of useful metrology tasks or parameter estimation tasks, you can indeed design such a guessing strategy where you don't get any bias. To write it down in more mathematical language, we can just put it in this form, and this is the starting point of our little derivation. So the first thing we're going to do is we're going to take the derivative of both sides with respect to theta of this no bias equation, just like that, and then we're going to evaluate this derivative. So the derivative first via the product rule acts on the probability distribution, and then it acts on theta. And then theta becomes a -1, and then we're summing over a probability distribution. So this term here just becomes -1. And then this term here, now we're going to use a trick, which is that the derivative of a function is equal to the same function multiplying the derivative of the logarithm of the function. So this is just a simple algebraic trick. Now, the second step is to move the -1 to the right-hand side and then square everything. So just very simple. And we're almost there now. The last step or the last trick is just to split this square into the product of two squares using the Cauchy-Schwarz inequality. So we're going to see that this equal sign will turn to a greater than or equal sign, and we've split this square into the product of two squares. The observant member of the audience will notice that this thing down here, that's the variance of our guess. So this is exactly the thing that we're interested in talking about. This is what we want to make small. And this thing up here is something that we will call the Fisher information. It was discovered by Fisher, who was a fellow at Gonville and Keyes many, many years ago. And it's a very central information quantity in basically all of statistics. And we can now see that because this is the variance of our guess, this variance is lower bounded by 1 over the Fisher information. So we now can like address this question of how well can we estimate theta. If we repeat our experiment n times, then the variance is lower bounded by 1 over n times the Fisher information. So if we want to make our metrology or parameter estimation experiment more precise, there are only really two things we can do in the setup. We can increase the number of trials, or we can design an experiment that has a higher Fisher information. So we can try to design an experiment such that these probability distributions, when you calculate the Fisher information, gives you a larger number. And these are the kind of two things you can do. This inequality, by the way, is like one of the most important inequalities in all of statistics and parameter estimation and metrology. It's called the Cramér-Rao bound. And I should also say that all of this is general. It applies to quantum experiments or classical experiments or whatever experiment you want to do. This is just looking at the probabilities. And today we're not going to focus on like how to increase the number of trials in an experiment. We're going to focus on how to make this thing called the Fisher information as large as possible. Okay. So as I said, all of the stuff on the previous slide was general. It applies to classical and quantum physics, but we're quantum people. So let's quantize this and see what happens. Our experiment now will be represented by a unitary matrix instead of just like some generic thing. And the unknown parameter is a parameter in this unitary. Here I'm going to make one assumption just to make our life simpler, and this is the assumption that the unitary is stones encoded. And what does it mean to be stones encoded? Well, it simply means that you can write the unitary as e to the I times theta times a, where a is a Hermitian operator. And this is a very, like, it's hard to say, but like most unitaries that people in quantum information care about satisfy this form. And the few unitaries that don't, you can often do parameter translations too, so that you get them into something that looks like this form. And the results I'm going to present, you can generalize, but just to keep things a bit simpler today, we're just going to assume this form, and it works for most scenarios. So our input states now in this quantum scenario is just some density matrix, rho naught. And when this density matrix passes through this unitary, the unknown parameter theta will be encoded in it. And then we can do a measurement. And here I represent the measurement by measurement operators E sub m, and these will generate probabilities. So running this many times, we will learn the probability distribution from this experiment. From these probability distributions, this is what gives us Fisher information, which was this quantity we wanted to be large in order to make precise estimations. So we can ask ourselves, how can we make this Fisher information large? Well, we could try to do the best possible measurement here. So in quantum mechanics, there are many types of measurement you can do. And already in 1994, this question was asked and answered in a beautiful paper by Brownstein and Caves, where they show that if you make the best possible measurement here, so you maximize the Fisher information over the measurement operators, you get a Fisher information that's given by this very simple and beautiful formula. It's just a trace of rho times lambda squared, where lambda squared is this thing called the symmetric logarithmic derivative, which is implicitly defined by this equation here. But usually when you have things that are like implicitly defined in terms of themselves, when you're trying to do algebra with them, things get a bit nasty, and they truly do in the case of Fisher information. So just to keep things simple for today's talk, I'm going to make another assumption. I'm going to assume that rho is pure. And if rho is pure, this maximized Fisher information simplifies significantly. So this might look like a less beautiful equation, but it doesn't contain this implicitly defined lambda. And because we've assumed the stones encoded unitary, when you evaluate this equation, you get something that looks like this. And now, again, like the kind of alert member of the audience will recognize what this is. This is just 4 times the variance of the generator of the unitary with respect to the input state. So Brownstein and Caves, they showed that if you're optimizing the final measurement, the amount of Fisher information you get out, which they call the quantum Fisher information, that's equal to 4 times the variance of A with respect to rho naught. So the second kind of question to ask is, okay, we've now optimized the final measurement. What happens if we optimize the input state? Well, that would just correspond to trying to make the variance of A as big as possible with respect to the input state. And one way of doing that is to choose the input state so that it's an equal superposition of the maximum and minimum eigenvalues of the generator of A. And after just a few lines of algebra, you will be able to show that if you optimize this equation of the input state, it just becomes the maximum eigenvalue of A minus the minimum eigenvalue of A to the power of 2. So we can immediately see here that like this is the maximum amount of Fisher information you can get from this unitary in this type of experiment. If you optimize your input state and your final measurement, this is as much as you can get. It's equal to the spectral gap of A to the power of 2. And I want to emphasize really that this is going to be a central quantity of interest in this talk. Okay. Just to summarize what we've looked at, so what is parameter estimation? You prepare some input, you do some experiment, you get some output probability distribution, which corresponds to information, and it's this information that allows you to make a guess of what the unknown parameter was. And most theorists so far, they've kind of focused on how to improve the input state and the final measurement to maximize the information you get out. But in this work I'm presenting now, what we were interested in was really not maximizing the amount of information. We wanted to maximize something called the information per cost rate. And what do I mean by that? Well, from an experimental perspective, say that you have an experiment you can do and that gives you 10 units of Fisher information. And this experiment is very simple to do. And then there is another experiment that's extremely hard to do that gives you 11 units of information. So I think many experimentalists would still choose to do the simple experiment simply because it carries a lower cost of conducting the experiment. And what could these costs be? Well, the cost could be like the actual cost of building the experimental apparatus, or it could be a temporal cost. So some experiments might take a very long time and some might be very, very quick. And this is the type of thing we were interested in, and we believe this is the type of thing that actually any real experimentalist who's doing metrology cares about. So let me just give you a simple example of when you have to care about the cost of your experiment and how to reduce that cost. Here is a completely classical experiment. The experiment is this box here. And the inputs the experiment can take are either gray or black balls. And with some probability p, it will receive a gray ball, and with some probability 1 minus p, it will receive a black ball. If it gets a black ball, the ball will just shoot straight through the experiment and nothing will happen to it. If it receives a gray ball, the gray ball will enter the experiment, and with some probabilistic model, theta will be encoded into its path. So if you run this experiment many times, you will be able to look at this output here, and from these angles of the balls, you will be able to deduce theta. And this output here, it corresponds to some Fisher information. But if we're looking at this carefully, we will see that actually these black particles that come out, they don't carry any information about theta. I said that they just shoot straight through the experiment. So now, if it indeed took a long time to measure these particles here, it would be beneficial just to block off the black particles and only measure these gray particles. And because we've gone from a scenario where we have some amount of particles to a scenario where we have less particles, the Fisher information that's left per particle in these post-selected on gray balls, it will be greater than the Fisher information per particle we had before. So this is just a simple example of how you can use post-selection in order to reduce your experimental cost, in this case, the cost of measuring each ball. You might say, but hey, you could just have started off with only gray balls instead of black balls, and then you would have the same kind of information per final particle in the output here as you do when you start with both and you post-select away the black ones. And that's absolutely correct. And this indeed is how this kind of phenomena is usually explained in classical physics. Your ability to post-select corresponds to an a posteriori improvement of your input distribution. And our work was really about showing that this kind of classical picture does not apply to quantum mechanics. But we'll get there in a moment. Post-selection in quantum metrology would look something like this. You start with a rho naught input state. That state then evolves according to some unitary evolution, which encodes theta into rho. And then you do a projective measurement. And the outcome that corresponds to this projector F, you keep. And the outcome that corresponds to 1 minus F, you send to a garbage collector. The idea here is that maybe your detector takes a very long time to measure the particles. So you want to make sure that every time you send a particle to the detector, that particle carries a lot of information. And what we wanted to know is how much information can you distill into these few particles that you're going to send to the detector. So we want to know what's the Fisher information or the quantum Fisher information of these post-selected upon particles. Here's just a beautiful schematic that Hugo made for the press release of our recent paper, where we're taking this kind of quantum circuit and translating it to something that looks more familiar to maybe an experimentalist. So our source of quantum particles is a laser here, and the laser shines light on your favorite molecule, and your favorite molecule has some unknown parameter that you want to measure. So this parameter is encoded into the light. And now here the light intensity is extremely strong. So say that if you put the camera here, it would saturate immediately and you would get no useful knowledge. So there would be a very high cost of measuring particles here because you would need a super good camera to do that. So we want to introduce this kind of quantum post-selection or a quantum filter, and we want to see how much information can we filter into just a few particles that then will reach our detector at a much lower intensity so that the detector won't saturate. Can we maybe send all the useful information into just a few particles and then send the rest of the particles to a garbage collector? So that's the kind of thing we wanted to ask. And in our paper, we find a theorem which says that this post-selected Fisher information, so the Fisher information in these distilled particles, it can never be greater than the Fisher information of an experiment that doesn't have post-selection, but that has the best possible input state and the best possible final measurement. So more in a schematic way, doing this post-selection, these particles here can never have more Fisher information than the particles that come out of this input and measurement optimized non-post-selected experiment in a classical theory. And here we take commutation as a notion of classical physics. So for example, in classical physics, you can know the position of momentum, you can know the position of a particle and its momentum at the same time because things commute classically. Whilst in quantum mechanics, things don't commute. So we will see in just a moment that this theorem can be violated by quantum mechanics. And it has to do with this thing that quantum mechanics doesn't necessarily commute. Okay. So in order to prove this theorem and to see that quantum mechanics can violate it, we need a mathematical tool that was crucial for making this proof. And that mathematical proof was something called the quasi-probability distribution. So now we're just going to step out of the mode of doing quantum metrology and parameter estimation for just a few minutes and refresh our memory of what quasi-probability distributions are. In classical physics, if you have a point particle, you can describe it perfectly in terms of its momentum, and so it's in terms of its momentum and its position. And if there's some uncertainty to what the position and momentum are of this particle, you can still describe it in terms of a joint probability distribution over its momentum and position values. But in quantum mechanics, famously, position and momentum do not commute, and you cannot describe a quantum system in terms of a joint probability distribution of momentum and position. What you can do, however, is to describe it in terms of a quasi-probability distribution. So here's a picture I've stolen from Wikipedia. It's showing the most famous quasi-probability distribution there is, the Wigner function. And as you can see, it's a function of position and momentum, and it kind of looks like a probability density function. But if you look carefully, you will see that at some parts, it actually drops negative, which of course a probability distribution can never do. The reason why Wigner introduced this thing is that it kind of has many properties of probability distributions, which allows you to describe quantum mechanics with this thing and then use a lot of the tools that were already there in statistical research. And then instead of using the Schrödinger equation, you can use this quasi-probabilistic formalism to do quantum calculations, basically. But the Wigner function is a continuous function. It's a function of continuous variables such as position and momentum. And most of quantum information processing is described in terms of discrete systems or systems that consist of multiple qubits. So these are things that the Wigner function really can't describe. And these are things that we were interested in. So we had to find a different quasi-probability distribution that allowed us to look at discrete observables. And here I've just written down like our discrete observables for today. A correspond to this Hermitian operator that drove our unitary, and it's just been decomposed in terms of its eigenvalues and eigenvectors. And F here will correspond to the projector on which we're going to do the post-selection later. And here F is the eigenvalue, and these F cats and bras are the eigenvectors. And later we will see that F will take values 1 or 0. But for now, let's just keep things general. So we want to find a discrete quasi-probability distribution that behaves kind of similar to the Wigner function, or that satisfies most of the kind of it should satisfy most of the probability distribution's axioms, but not all of them. So if you saw Jacob's talk last week, you will remember a few of these things when he talked about quasi-probability distributions. So for example, you want them to sum to unity. And if you have a quasi-probability that depends on two values, A and F, if we sum away the F value, we want to be left with the probability distribution, so a classical probability distribution over the A values, so that if we marginalize our quasi-probability distribution, we should get the classical probability distribution that explains the outcomes of real experiments. And this is done by this distribution called the Kirkwood-Dirac distribution. It was first discovered by John Kirkwood at MIT in 1933, so just a year after Wigner found his continuous quasi-probability distribution. And it takes this very simple form. It's just the product of these two sandwiches, basically. And you will see that this guy satisfies these properties, but it's not a classical probability distribution because it can take negative or even imaginary values, which of course classical probabilities can't. And just again, reiterating some stuff Jacob said at last week's meeting, that the Kirkwood-Dirac distribution has been used to study non-classical physics in many areas. So you basically can use it as a tool to find when there is a quantum advantage. So if you express your formula of interest in terms of a Kirkwood-Dirac distribution, and you see that you can do better things when it goes negative, or if it's imaginary than you can when it's real, then you know that quantum mechanics can give you an advantage, because classically this thing becomes real and lies between 0 and 1, but quantum mechanically it can be negative or imaginary. So let's get back to the kind of main topic of today, which is quantum metrology and parameter estimation. Just to remind ourselves, we wanted to know how much information we could distill into these few particles that we send to this expensive measurement device. And after quite a bit of algebra, it's possible to show that the expression for this information carried by these particles is given by this guy here. Here, F is this post-selected on projector. A is the generator of this unitary. Rho is the state that comes out of the unitary. And P sub theta super PS, so this thing here, that's the probability of succeeding the post-selection. But looking at this thing here, it's not really clear whether or not this is a good thing to do. Is this more information than this spectral gap to the power of 2 we found before? And in order to investigate it, we decided to express it in terms of a quasi-probability distribution. The one I showed you on the slide before had an F, an A, and a rho. But here we have a big F, a big A, a rho, and another big A. And we found that basically the quasi-probability distribution that does the job is this thing here, where you have an F eigenvector and 2 A eigenvectors that both correspond to the A generator. Expressing this equation in terms of this, and I'm not going to go through all of that algebra, you basically get this, you get this formula here, which for someone who's used to doing statistics stuff, it kind of looks like a quasi-probability version of a Bayesian update of a variance, except for this little prime here. So we now kind of wanted to see how large can this thing get in a classical scenario, and how large can it get in a quantum scenario? So to address the first question, we'll assume that the quasi-probability distribution is classical. That means that the quasi-probabilities will lie between 0 and 1. And then we want to see if we can bound this guy. And I'm actually going to not go into the details of this, but it turned out that in order to do this calculation, it was crucial to assume that the eigenvalues of A were all positive. And in our paper, we do the simple calculation where we add a little shift to the eigenvalues, and then we show that actually you get back to your original Fisher information. So in fact, you can assume that all of these eigenvalues are positive. So we can assume that all of these eigenvalues are non-negative, so they're greater than or equal to 0, and then we can just use statistical tricks in order to bound this thing. So I'm not going to go into the details of this, but after you have gone into the details of this, you can show that classically the quantum Fisher information of this post-selected experiment is upper bounded by the spectral gap to the power of 2, which was this maximum Fisher information that we could get out of this non-post-selected experiment. So this is the ultimate proof of how post-selection cannot really help you in a classical scenario. Well, it can help you, but it can't help you more than if you'd done the best possible non-post-selected experiment. So just to put this in mathematical writing, the post-selected quantum Fisher information can never be greater than the spectral gap to the power of 2 if the quasi-probability distribution is classical. But in our paper, we also show that if the quasi-probability distribution tips to negative values, you can have post-selected Fisher informations that indeed surpasses this classical bound and distills more, or non-classically more, information into these few particles that we will send to our costly detector. And just to connect back to the discussion in the beginning of the talk, these kind of very high or non-classically high rates of information we can get into these particles, this is what allows us to improve the information to cost rates. So this basically shows us that quantum negativity is something that can give us an advantage if we care about the cost of experiments. The question then is how much can, and I'm really getting to the end of this talk, but the question is how much more information can we push into these particles? In our paper, we look at a very, very general experiment where the dimensionality of the Hilbert space is greater than or equal to 3. And we just focus on 3 of the eigenvalues and eigenvectors of our generator A. The smallest one, the biggest one, and one in between. And then we show how to design this post-selected metrology experiment in order to do something nice. We assume that the post-selected on projector is a sum of rank 1 projectors, where F1 and F2 are given by these equations here. And don't look at the details of this because things are going to get a bit nasty soon. But take-home message is that, like, knowing what the generator is, you can use that knowledge in order to decide how to define F1 and F2. And then we also show how to choose the best possible input state for this experiment. And essentially, the best possible input state, you start off with the state in this curly bracket here. And phi, that's just an experimental parameter that you later will have to tune carefully. And then on this state, you apply the reverse of your unitary with your guess of what theta is. So you actually have to have an initial guess of what this parameter is in order to do this effectively. And this is what the state looks like. Again, don't pay too much attention to this because the Fisher information will take this absolutely super complicated form. But if you then take the limit of this parameter delta, which is the difference between the true value of theta and your initial guess. So if your initial guess approaches the true value of theta and you tune this experimental parameter phi to 0, we show that the probability to succeed the post-selection goes towards 0 at the same time as your Fisher information that goes into these very few particles tends towards infinity. So let me just iterate that. Like, you can use this scheme to show that you can tune so that you only get very, very few particles going to the final detector at the same time as you're condensing the information they carry into enormous amounts. But then you might say, hey, this is kind of like cheating because you're assuming that your initial knowledge tends towards the true value of theta. So if you already had perfect knowledge of what theta was, then you already had infinite Fisher information. So that's kind of like cheating. So to address that, we did a bit of numerics where we put minimum eigenvalue -1 and maximum eigenvalue 3. So the spectral gap is 4. And the Fisher information you should be able to get in a non-post-selected experiment per particle is 4 to the power of 2, 16. And then here we plotted, so on on this height axis here, this is the post-selected Fisher information per initial Fisher information. So you can think of this kind of like the post-selected Fisher information divided by the Fisher information you had when you made your initial guess. And then here we have these two parameters, delta theta and phi. And if this was an optics experiment, these are kind of the scales that you could, in the state-of-the-art experiments, tune your polarization rotations, for example. And we show that in these kind of, at least on paper, viable experimental regimes, you should be able to get absolutely enormous improvements to the amount of information that goes into the particles that you send to your detector. So we've basically shown that quantum mechanically you can distill a lot of information into very few particles, which is something that wasn't entirely understood before and which definitely wasn't understood in terms of the framework of quantum metrology. Just to conclude, post-selected metrology can give you better information to cost rates, and this is true both classically and quantum mechanically. And then we use the KD distribution, Kirkwood-Dirac's distribution, to show that in quantum experiment, post-selection can give you non-classically large information per cost rates. So basically, post-selection can be better quantum mechanically than it can classically. And in the end, we saw these numerics of that you can almost always get an arbitrarily high amount of post-selected Fisher information, at least if you're in dimension 3 or larger. And yeah, with that, thanks for listening. Again, here's the nature link and here's the archive link. And I should mention that this kind of prototype optics device is actually being built as we speak at the University of Toronto under the supervision of Aephraim Steinberg, where they're going to investigate basically in a realistic experimental system, what kind of use could this give us, and what's the real fundamental nature of these negative probabilities. So yeah, thanks very much for coming and for listening.
Great, thank you very much for this presentation. So if you have any questions, please write them in the Q&A section. The chat is disabled for this meeting, but the Q&A section, you can ask questions there. We already have one, but this person asked a question anonymously. So if you could just type in the Q&A section your name, I could promote you to a panelist, and you could ask your question. So we have another question here I will promote. Okay. Participants. Okay, promote to panelists. So if you can activate your camera and your microphone, and you can ask your question, please.
Hi, sorry. I'm in a really bad lighting, so you would only see my shirt.
Okay.
Yeah. My question was regarding the slide that you have up now, and I think my question just disappeared, so I don't know if I'm going to say the exact same way I asked. But then during your talk, you mentioned that you were able to select the rubbish from non-rubbish information and discard the rubbish. And then also, what was the second part of the question? I don't remember the second part of my question. Where
second part was, how are you specifying the unknown measurement of the molecule?
Yeah. So and also, yeah, since yes, in the beginning you were like, oh, that if you're measuring a molecule that is like you're measuring some measurement of the molecule, then you're able to like specify. And I'm like, okay, so if we're not knowing what we're measuring, how are we specifying it, or is it just arbitrarily covered in the negative quasi-probability? That was it. Thank you.
Okay, let's see if I've understood your question correctly, but essentially you're saying like there's something unknown about this molecule, so how do we know what we're measuring? So I think what I've been focusing on today is something called single parameter estimation, where we assume that there's just one thing that we don't know, this parameter theta. So we would have to know everything about this molecule except for one thing, which of course is a very theoretical view. But for example, you could have a solution where a molecule induces a polarization rotation of the light passing through, and you want to know what is this polarization rotation. And so then that would be your unknown parameter theta. But in the kind of theory of this, you assume that you know what the generator, the Hermitian generator A is. You just don't know the strength of the interaction. So another kind of experimental example would be that you're passing an electron through a Stern-Gerlach device, and you know exactly what the Stern-Gerlach device does, but you don't know the specific magnetic field strength in the system. So then that specific magnetic field strength would be what you're interested in. If you're interested in more than one unknown thing at the same time, there's a whole plethora of literature on something called multi-parameter estimation, which we're actually working on a follow-up paper on that. But just to summarize it, things get much more complicated and tricky, both theoretically and experimentally, if you have more than one thing that you're interested in at the same time, especially if you don't commute.
What about the specificity part?
So would you mind repeating that part?
What did I say? I don't have my original question up again. Sorry, Dr. Hugo, would you mind repeating the last part of my question? You're muted.
Sorry, I think that was the last part, right? How are you specifying unknown measurement of the molecule since it's unknown? The first part was, how are you selecting the non-rubbish info? Okay, so the first part then, I mean, I think the short answer, which might not be a very satisfying answer, is that it's a bunch of maths that tells you how to do it. And in one of the appendices of our paper, we
we show how you can use the knowledge of your generator in order to design this kind of quantum filter that will allow you to do that. And before, in our original paper, we had some ideas of how to do it, and we showed that in principle you can do it in dimension 3 or larger. What a nice result of this experimental work with the University of Toronto is that a very clever PhD student in their group has actually shown how this can be transformed to systems of just dimension 2. And in such a way that you actually never lose, at least in theory, you never lose any information, but all the information can go into the few particles you save. But the kind of workings of it's very mathematical, and I struggle to give a good qualitative.
Was it the inversion bracket? Because I did take a glance at the paper. Was it the inversion bracket where if it's a value, it's 1, if it's not, if something else is 0, was it that one?
Yeah, and that's basically it.
That's fine. Yeah, okay, then I understand it. And then my last one, then during your abstract of the talk, you said that you can see how you can apply it to like to technologies. And I was wondering how are you applying it to technologies? I know that you said that this is being built, but I feel like this, like, is this more of an experiment or is that a technology? Like, I know you're saying like, oh, if you're going to study a molecule, but then like, would you be incorporating it into a beam, like a low photon dose? Or...
Yeah, so to see if this is actually useful in real technologies, we have to do an experiment. And the idea is that, like, in many photonics experiments, you have detectors that saturate, and it's very cheap to produce light photons, but there's usually a temporal cost associated to measuring them in terms of the dead time that photon detectors have. So every time your detector detects a photon, it will go idle for some time. And the idea is to see if we can like find some very general kind of solution to how to make sure that every time your detector gets a package of light, that package of light carries a lot of information. And the hope is that this will be able to solve many saturation problems and improve precision in many experiments where your detectors saturate. But it's to determine how well that can actually help real technologies in this experiment.
Okay, thank you.
We have another question by Niall Devlin. If you can ask it again for the crowd, please.
Hi, David. Thanks for the talk. It was really interesting. So sorry if my terminology isn't all good in this question. Please correct me if I'm wrong at any point. But usually we talk about, well, traditionally sort of entanglement has been mentioned as this quantum resource that can quantify the sort of, in layman's terms, the amount of information held in a quantum state. Is there a link between the Fisher information that you might get in an experiment and the entanglement that you're using in these pure states?
Yes, this is a really good question. And I think the short and unsatisfying answer is that, like, I haven't looked at this. But I can say a few things. I know that Nicolas Gizin, I believe he's in Switzerland now, he's been working on connecting Fisher information to entanglement and seeing how entanglement and Fisher information are related. And disadvantage, so quantum negativity is a separate resource from entanglement, I should say. So the fact that we can do this is not necessarily bound to entanglement. It's bound to this non-commutation of operators in quantum mechanics, but there are other connections to be made. So this Kirkwood-Dirac distribution here, for example, this you can use in order to measure something called quantum information scrambling. And usually the way you measure quantum information, so what is quantum information scrambling? You have a multi-particle system, and that starts off in a separable state, and then you inject information on one of your particles by like doing a single qubit rotation, maybe on one of the qubits in your lattice. and then you turn on a bunch of interactions between the particles, and these will entangle all the particles, and that will scramble, so to speak, the quantum information that was originally on one node. And this kind of behavior is usually measured by something called an out-of-time ordered correlator. That's a measure of how well your experiment is scrambled. The problem is that out-of-time ordered correlator, if you have a system that decoheres, that will give you something that looks like a very quantum mechanical out-of-time ordered correlator, but in fact it's the opposite. It's your system that has decohered. And there are a few papers by Justin Dressel with collaborators from last year and a few years back, where they instead used this Kirkwood-Dirac distribution that you can measure. And then they use this in order to design another measure for quantum information scrambling. So this Kirkwood-Dirac distribution is something that actually can signal quantum information scrambling, and quantum information scrambling is like a great way to see if your quantum computer is entangling in a good way and scrambling information. So this thing here can definitely be connected to entangled states, but negativity, which is the resource of today's talk, is not something that's inherently that requires entanglement, because you can have a negativity in a system that's just you can have negativity in a single particle system, which is not entangled with anything. Does that answer your question?
Yeah, that was a good answer. I think I need to look at this Kirkwood-Dirac distribution a bit more to really understand how it might be used for quantum information scrambling, because yeah, I'm not too familiar with it. But
yeah, I think I can send you a link. So the best kind of paper, I think, is a PRA from last year or possibly 2 years ago by Rasse and Justin Dressel, where they give a good overview of what is quantum information scrambling, and then they say, hey, this is how it was measured usually, and this is how we're going to measure it now. So that might be like the best go-to paper.
Yeah, maybe. Great. Okay, thank you, David.
All right. I think I just have a short question as well, and this will probably conclude this talk. But related to the talk we just heard earlier with Hitachi, which was also on metrology, what kind of integration steps are needed to use this protocol on currently existing metrology devices or setups? It seems like it's mostly post-processing or post-selection. So what kind of modifications would you expect to need for current systems?
So first of all, it's about finding the right system. So we've been focusing on these systems now where the measurement is very costly. So you get an advantage if you can condense information into a few particles. But the Hitachi talk we just saw, they used NV centers as sensors, and then the preparation state is actually something that can be very costly. And in such scenarios, this is not beneficial, or it's definitely not as beneficial as we've seen. So the first thing is to find a kind of an experimental system or technology where your input system can be prepared very cheaply, and also where this post-selection can be done very cheaply. For example, in optics, it can be done by using a beam splitter and sending half the state to, like sending some of the particles to a garbage collector. And then the question is how robust is all of this to noise? Because obviously, if we're doing these very, very delicate operations and transferring, distilling information into these very few particles, going from many, many particles to a few and trying to keep the information, you become very, very susceptible to noise. So I think there are many questions to be answered before we can see whether or not this can be implemented in real technologies. And the reason why we went to optical systems, first of all, is because it kind of ticked the boxes for cheap state preparation and then cheap post selections and potentially expensive measurements. But I think the first step is to see if it helps us in these scenarios, and if it does, then that's the time to kind of think of how could you potentially use this in systems where you use quantum dots as sensors or things like this.
All right. Thanks, and thanks for this really interesting talk, and thank you everyone for your attendance and your questions. So now we're just going to move on to a regular group meeting. So everyone who's member of quantum information or new members of quantum information, please stay on, and everyone else, we'll see you next week.